There's two of them. So I do everything on my screen here. So I have everything on my screen. And then this program is called OneNote. And you should have access to it if you need it. But it lets me write on my screen like that. And so you don't need to use it, but everything that's in the class is in this notebook that I'll share with you. And so I have all the content, like I have various problems we worked on in class here, along with information. And if you go to Moodle and log into our site, you should be added to our, oh, it's invalid, huh? Okay, let's try again. You should be able to log into our site here, and you can click on this playlist for YouTube. And I've recorded all our classes. So if there's anything you missed, you can go and look at it. Yeah, we use a lot of technology. I learned all this because of the pandemic. I had to learn how to do everything remotely and digitally, and I'm just like, you know what? We're gonna stick with this, at least for this class. Here's a handout that I gave everyone. Actually, does anyone else need the graph sketching handout? Because I think we were missing a few people. Connor wasn't here. Do you have a game? Was that it? Or I forget. You're just like I wasn't coming to class that day. As a student who used to skip class occasionally, I am in no position to condemn. Do you need one, Keelan, or do you think so? Maybe?
I'm looking.
Jerry, do you need one? Did you get this last class? You did? Okay. Okay. You should never skip class, of course. Never do that. Okay. But all right, great. All right, so just a reminder, there's an exam on Friday. I posted a review sheet for that. There is a homework. It is a very short problem set for Wednesday. The web work, though, is a bit long, but it's actually just finding absolute maxes and absolute mins for the most part. So you find where the derivative is 0, you get your critical point, you plug the critical point into your function, you plug the endpoints of your interval into your function, whichever is biggest is your max, whichever smallest is your min. If you run into any trouble, please let me know. I'll be glad to help you work through it quickly. All right. So let's just recap what we were doing last time. We were going to begin the process of graphing functions by hand. And although this is technically something we don't need in our modern era, it is useful for sort of reinforcing a variety of concepts in calculus. So that's why we do it. I'd given this handout that sort of described how we are going to go about plotting this function here, x to the 4th over 6 minus 2x squared plus 4. I mentioned that this x to the 4th over 6, you can think of that as 1/6 times x to the 4th. And then what we're going to do is we are going to find the critical points of f to begin with, because we want to figure out where this function is increasing and decreasing. And so last class we began with that. I took the derivative of f. I got 4/6 x cubed minus 4x, and I factored an x out of both terms. And I simplified the 4/6 to 2/3. So I got a 2/3 x squared minus 4 here. And we went about figuring out when this quantity could be 0. And it could be 0 when x is 0, or it could be 0 when this thing in parentheses was 0. And so we went through the hard work of figuring out that that happened at plus or minus square root of 6. So we have 3 critical points. And we were about to officially figure out our increasing, decreasing intervals, and I kind of hurried our way through it. We set up our interval negative infinity, negative square root of 6, negative square root of 6 to 0, 0 to square root of 6, square root of 6 to infinity, and we plugged in different test values within each of these intervals into our first derivative. And so when we did that here, we got a -6, positive 10/3, negative 10/3, positive 6. And that's good because now we can classify our function as being increasing or decreasing on each of these intervals. So which is it here on this first interval? Increasing or decreasing? Decreasing it is. Then increasing because it's a positive 10/3, and decreasing because it's negative, and increasing because it's a positive. All right. Now the next task is to identify any of the local maxes or local mins that exist in this function. Now remember that a local max and a local min can only occur at a critical point. And so the only places where we could have these occur are at -√6, 0, or √6. So let's start with -√6. What sort of thing do we have there? Is it a local max, a local min, or neither? It is indeed a local min. You can imagine you're trying to make sure I draw this. I've completely lost track of what left in it. You can imagine the function going, it's decreasing, and then after that critical point square -6, it goes to increasing. So it is a local min. Here, I'll write it down here. Local min at x equals -√6. All right, let's take a look at the next one at 0. What sort of thing do we have there? Local max, that's correct, because it goes from increasing to decreasing. Local max at x equals 0. And last of all, we have positive √6. What do you think? Min is correct. All right, there we go. So we were able to figure out where the local mins and local maxes are. Now, in the past, I was content to just know where these were on the x-axis, but for plotting purposes, we're also going to want to know what the corresponding y-coordinates are. Oh, I'm sorry, your Wi-Fi is really bad. Well, hang in there. It's fine if you pop in and out as a result. You can always try turning off your camera if that helps. All right. So what I need to do, in addition to computing where the local maxes and local mins are, I'm also going to want to figure out what my function is at these points. So what is, I think somebody's unmuted right now. No, nobody's unmuted. What's going on? Do you got, Abigail, do you hear that too? Yeah, weird. Huh. Maybe it was Sydney. I don't know. Could have been. Oh, nope, she's out. She's out. Oh man, I didn't mean to scare her away. All right. All right, so we've got, we want to figure out what our function is at -√6, because in addition to knowing the x coordinates, we'll need to know the y coordinates. So I'll go back up here and look at my original function. I can see it right there. It's x to the 4th. Let me grab a picture of that so I can have it handy when I plug stuff in. There we go. And let me paste, drag this over here, shrink it down a little. There. That makes sense. So for this particular problem, oh man, I just accidentally, the technology is failing. Okay, there we go. All right. For this problem, I can actually evaluate this one by hand, which is nice. So what will happen when I plug -√6 into this thing? Does anyone want to guess what's going to happen? Well, I mean, guess. I mean, what's -√6 to the 4th? 36. It is 36. So I'll get a 36 over 6. Here I'll have a -2 and this -√6 squared. So I'll get a -12 and then a +4. 36 divided by 6, I know what that is. That's just 6. So I'll get a 6 minus 12 plus 4. And so what I get is -2. And can you guess what f of positive square root of 6 is going to be? It's going to be 2 as well. Well, negative 2. It's going to be negative 2. Yeah. Yeah. So local mins, that's the value there. All right. So if I were to plug it all in, dot, dot, dot equals negative 2. All right. What's f of 0 going to be? 4. All right. So I know this is a lot of writing I'm doing, and I didn't necessarily give you enough space, but I'm going to sort of summarize what we just did here on the side. Basically, what we have is a local min. The local mins are at, on one hand, they're at negative square root of 6, negative 2, and negative square root of 6, or positive square root of 6, negative 2, right? So those are the two coordinate points of my local min, and the local max is at 0, 4 right there. So I'm just going to kind of remember that because I'll need that later when it comes time to plot this. So I'll just stick that on the side here. Yeah. So all that follows right there. So just to recap, we classified the critical points as local mins or max. We then plugged in these x coordinates into our original function f. We got y coordinates. For negative square root of 6, the corresponding coordinate is negative 2. Positive square root of 6, it is also negative 2. And for 0, it is 4. All right. Now you're going to have to do this for the second derivative. So we're going to repeat this process essentially. Find the second derivative of your function. I recommend differentiating this portion right there. Figure out the derivative, find the second order critical points, find where the function is concave up and concave down, then find the inflection point or points, as the case may be. And then once you've done all that, we can get ready for plotting. All right, so go ahead and try that out. I know that's a lot of stuff to do, but I believe in you. And I think I have a few homeworks to hand back that I forgot to hand back earlier. So let me get those. This stuff make more sense? I don't know. Okay, all right. I've been looking at it this morning. I'm going to continue working on it this afternoon. Been trying to figure it out. Okay. Like walking around in circles here. Man, I've been meaning to buy some tissues, but I don't have any. There's some paper towels over there if you're, or you could use it, try using some toilet paper. That's that's the next best option. Here you go, April. I forgot to give that back to you last class. Sorry. You were here and I just forgot. All right. Okay, welcome back, Sydney. I just read the chat. Just read it. How goes the second derivatives?
Almost a second. But
How come I'm not remembering? Yeah. So the nice thing about 12 over 6 is it simplified a lot.
okay.
Not quite sure what you're doing. Yeah, so you took the derivative. Not sure about this 1/6. Oh, I see. Yeah, the 12. Okay. And once you, yes. Okay, good. You're good. You're good. Keep going. I did not mean to startle you.
That's
Yeah, I'll give you time. No pressure, no pressure. By the way, online students, if you wanna check if you have correct second order critical points or things like that, feel free to just unmute and ask away. I can hear you while I walk around the classroom. Looking to get started on this? Okay. You do not have a pencil. Oh, well, wait, I've got more pencils for you. Okay, so I'll get a little chain like at the bank and we'll leave it chained here. And it'll be like your special pencil. So the first derivative, right? That was 2/3 x squared, x cubed, sorry, minus 4x. So I've taken the second derivative here and I've gotten it down to 2x squared minus 4. And I factored a 2 out of everything so that I just get x squared minus 2. Now, does anyone know at what values does x squared minus 2 equal 0? Yeah, that's a positive plus or minus square root of 2. So negative square root of 2 and a positive square root of 2. All right, just want to make sure you're not barking up the wrong tree on that one because it'd be a real shame, huh? Real shame to get that wrong and then you make your table and it's all wrong. Yeah. Why can't you just, cause there's only, there's no X on this one, on the 4. Yeah. How's it going, Megan? Good, yeah, okay, yeah. Good work. How's it going, Jack and Josh? And did you find everything? Okay, yeah. Oh, okay, intervals of concat. So what you're gonna do is you're gonna set up intervals like this, but it'll go from negative infinity to negative square root of 2, and then from negative square root of 2 to positive square root of 2, and then positive square root of 2 to infinity. I'll walk you through the process in a little. For now, if you want to just watch, I understand. If you're thinking, is this all we're gonna do for the rest of the course? Just do intervals. No, no. things are gonna get a lot more interesting after this section is done. We're gonna cover a topic called optimization, one of the most useful applications of calculus. And all you computer science majors out there, this is actually optimization is in some sense the key to machine learning and artificial intelligence these days. Now, what we'll do in this class isn't going to be exactly the same as what's done there, but really, when you train an AI system, you are actually trying to find a local min of a huge function, not in one variable, but in like, billions of variables. And so it's pretty fun. All right. I got my intervals. What do you think is a good test value to plug into the second derivative here? Obviously, it's got to be negative. 2, -2, yep. All right, and so if I plug -2 into there, right, I'm going to get a 2 times 4 minus 4. I'll get a 4. I think 0 is a good value to plug into there, right? And then my second derivative, I'll get -4. And last, I'll plug in 2. And that'll give me +4 again. And so if I wanted to classify the concavity of each of these intervals, this one would be up, down, and up. All right, those are our intervals of concavity. Now the next part asks us to find any inflection points. Where, does anyone see where there are inflection points? Where are they at? You kind of have to look back at your concavity table to see it. Oh, what is an inflection point anyway? So I want to remember what those are. Yeah, flips concavity, right? And they can only happen at the second order critical points, right? So the potential places for inflection points are -√2 and +√2. Are there inflection points there? Yeah, yes, there are. See if I, oops, didn't mean to slide you there. All right, if I look at -√2, -√2, to the left of -√2, it's concave up, and then to the right, it's down. And then at +√2, it's concave down to the left and up to the right. And so in this case, yeah, I have inflection points at both of these because the concavity switches. And √2. And just as before, it's going to be really helpful for plotting purposes for me to actually, plug in these values into my original function. And because my original function is so far away up there, I'm going to grab a copy of it and paste it down here so I can work with it. There we go. There's the original function right there. So I'm going to plug -√2 and +√2 into this. All right, I'll get -√2 to the 4th over 6 minus 2 times -√2 squared plus 4. All right. And if I look at the 4th power of this, this will give me in the end, just a 4 over 6, if I can do my arithmetic correctly. And this will give me a -4 and a +4. I'm left with just 2/3 right there. And does anyone want to guess what f of +√2 is? 2/3. And so now I've got something very good here. I've got inflection points at, one is at -√2 and 2/3, and the other is at √2 and 2/3. All right, there we go. So we're able to identify where our inflection points are. We're able to identify where our local max and min are. We're able to figure out where the function's increasing, where it's decreasing. I have this one additional thing called the asymptotic behavior of f. I'm going to go back to it in a little bit, okay? But for now, I'm going to take all that information we've gleaned and we are now going to start plotting this thing, okay? That's what we're going to do. This is the moment of truth. Can we plot it correctly? Now I have this color coding system I devised, which I was really quite proud of, and I've since forgotten what it is. There we go. Yeah, color guide. Oh yeah, there we go. So what I like to do is I like to begin by marking off where my local extrema are. That is where my local max and my local min is. Now, to make it easier for us to remember where they are, I'm going to mark them in red. And so I'm going to just sort of grab this bit of information I had that I already computed and bring it down so we have easy reference to it. I don't know what just happened there. All right, there, I forgot to click. All right. So here I've got my local min and local max at these points. Now, what is square root of 6 approximately? Does anyone know what square root of 6 is approximately? 2.449. I'd say that's about 2.5 in my book. All right, so I'm going to look at around 2.5 here, right? And I want a local min with around a little less than 2.5 and a y coordinate of -2. And so this right there, that red dot right there, that's going to represent this point right there. And I'll have a corresponding point at negative square root of 6 minus 2. So that'll go right about here. And then the other local extrema I'll have is from 0 to 4 at 0, 4 right there. So I'm going to try to plot a curve that's going to have this as my local max and this as my local min and local min here. And I think it's pretty clear from just the positioning of these red dots that my function is going to be increasing between these two dots, right? Decreasing here. And as you may recall, it increases afterwards there and it decreases there. I'll pull that up later. All right, so I've marked off my local extrema. The next thing I like to mark off are my inflection points. So let me recall what those are. So here I wrote them down. So let me put those here for easy reference. There we go. That's nice. I mark those in purple. There we go. That's purplish enough. All right, square root of 2 is around 1.4. So around square root of 2 2/3. Where would that be? I'd say that's maybe right about there. That might be a little too, this isn't purple enough. We need more purple. There, slightly darker shade. They look too similar on the screen there. All right, there. That's about 2/3 on the y-axis if you go across right there, and about 1.4-ish there. And then I'll need another one kind of mirroring it on the other side. This mirroring is kind of a coincidence. If you're wondering, does it always do this? No, it only does it because I tried to pick a nice problem. That would be easy to work with algebraically. All right, so those are my inflection points. Next, I am going to look at my concave up and concave down intervals. I'm gonna actually just copy and paste them over here. So those are the ones we just did right here. Actually, maybe I'll get the increasing, decreasing ones as well. For now, I'll just do concavity. I find it helpful. You don't have to do this, by the way. You don't have to do any of this color coding. I just do it because I find it helpful. Actually, you know what? Here, let's I need all the real estate I can get, right? I don't need to remember how I got these concavity results. I just need to remember what they are. There. That looks nice, huh? Yeah, shrink that down. All right. So what I've done in the past, and if I look on the notes I share with you, I mark concave down in orange and concave up in green, but I don't highlight it. What I do is I kind of just highlight the x-axis where this is. So here I could see from negative infinity to negative square root of 2. I want concave up, and so what I do is I kind of take my pen here and I just kind of highlight. See what I did there? That's like a signal to me on the x-axis. It's telling me, look, it's got to be concave up on this interval. That's a little too squiggly for my taste here. Let's take advantage of OneNote's autocorrect features. Yeah, oh yeah, that looks really nice, huh? Way to go, OneNote. Can I scoot you down a little? Will you let me put you right on the axis? Yeah. Oh wow. Perfect. Good job. Good job, OneNote. All right, and then I can play the exact same game here. I know this interval has to be concave up. That one actually I drew better. And then this is sort of my concave down interval right there. All right, and so now the goal is for me to, here, let me grab the increasing, decreasing intervals as well. So I have those just as a rough guide in case I need them. Here we go. You know how long this would take before when I did this on a chalkboard? Take forever. And be like, oh, let me rewrite all this. Yeah, I just kind of drag and I drop and I move it. It's very nice. There we go, increasing there. That'll be handy to have. Handy to have right there. Okay. So let's take a look at this. Concave down here, right? Concave down between negative square root of 2 and square root of 2. I could see that it should be increasing kind of to the left of 0. So I want that curve there to be local max. And so what I do is I just kind of lightly put like a curve like that right there. This meets my requirements. It's concave down right there. It's increasing to the left of 0, and I need it to then be concave down and decreasing afterwards. And so I'll kind of draw it like that. Doesn't have to be perfect, but it's nice if it is. All right, there we go. And so you see what I did there? So I knew that there was a local max here, so I drew my curve to kind of make that a local max. And I know these have to be local mins, right? And so at this point, I'm going to have a concave down shape. Something that's kind of like that. That's nice and concave down on both sides. If you're like, maybe you could draw this better than me. Okay. And the question now is, this is a good sketch. The question now is what happens to the right and what happens to the left? Like, it's not obvious what should happen. We know it needs to be concave up, right? Out here because of that green portion right there that we can just barely see. And we know it has to be increasing because this is around square root of 6 right there. But it's not clear, obviously, whether it's going up, is it going up like that, or is it doing something else? Is it kind of just going really slow? Like, what is it? What's the sort of general shape here? And for this one, it's not a big deal if you don't get it right, but I do find it helpful to discuss briefly the idea of limits at infinity again. So do you remember that fun-filled topic of limits at infinity? Where we take the limit as x goes to positive infinity and x goes to negative infinity. Remember? Yeah, it was like your favorite topic last semester. All right, well, the good news, it's back. It's back. It's back with a vengeance. I mean, no, it's going to be fun. The good news is I try to keep it relatively chill at first. Okay, so we want to figure out what happens when x goes to infinity here and to negative infinity of this function here that I have written down. The limit as x goes to infinity of my function f of x that I have written down right there. Now, if you recall, to figure this out, there's really only one term we needed to look at, and that was the very first term, this x to the 4th over 6. And so what we need to do is figure out what our n is and what our a sub n is. What is this power of x here and what is its coefficient? So anyone think they see what it is? What is our n? 4 is correct. And what is the a sub n? 1/6 is correct. All right, so that's that. We just had to figure that out. And once we figured that out, it's for taking the limit as x goes to infinity. All we need to do is determine whether this a sub n is positive or negative. Is 1/6 positive or negative? It's positive. And so this goes to positive infinity for that reason. That's it. Now, when x goes to negative infinity, things get a little bit more complicated. When x goes to negative infinity, we have to look at what our n is. Is our n even or odd? In this case, 4 is even, right? So we are going to use this formula here for this problem. And our 1/6 is positive, and so when x goes to negative infinity, we get yet again a plus infinity. And so that sort of tells us that this function is growing. It's growing up high. It's not sort of plateauing as it moves off to one side. And so it's fair to infer that we could have a curve that kind of roughly looks like this, that it goes back up. It's going to positive infinity as we move this way and positive infinity as we move to the right. Isn't that thrilling? Now, it turns out that in reality, if you want to see what this really looks like, what it really looks like is actually it's much steeper. It's this steep here. But I'm not too picky about that. We're looking for qualitative sketches, sketches that are roughly right. So more like that area. All right, that's a pretty decent plot of this function right there. Okay, I don't want to clean up too many sketchy lines there. Okay. All right, so there we have it. We got a nice little function. So I have more problems for you to do just like this. I don't break it down into parts like I did before, but I do give some steps right here. Step 1, find critical points. Step 2, find intervals where it's monotonic, identify local extrema, find second order critical points, find intervals of concavity, identify any points of inflection, figure out that asymptotic behavior, plot the local extrema inflection points, and then connect it all with a nice curve. All right, so here is number 2 right there. Have it. You probably can't fit all the work on the worksheet. You'll just have to work on a separate piece of paper. But have fun with that. I believe you can finish it in the next 20 minutes. Oh man, we're gonna start integrals soon. Anyone doing integrals in their classes yet? Do they do it in your classes? Integrals? No. We're doing algebra. Okay, all right. We'll do it. They don't know how to do the question. Boy, who's your chemistry teacher? Is he like losing his mind? Like if I were Rally, I'd be losing my mind.
No, like people are like, do we have to learn how to do this? The hardest question. It won't even be on the exam.
What?
I know it's crazy.
Hold on. Quadratic formula. You gotta know that one. My friend who like he he failed college lots of times. Like he was not good at college. He was my best friend growing up. He'd go to community college and he'd fail all his courses every semester, but they had to accept them because it's community college. And he knew the quadratic formula. He knew it. He also had to do summer school in high school every year, because he'd fail his high school classes too. He was an absolutely terrible student. We had a lot of fun together, but not a good student. But eventually, so here's an interesting thing though. So he eventually moved out of his parents' house, which apparently was the key to his success in life, because it was not a good environment. He moved out, moved in with some guys. They all went on a diet. And then he got into cycling. And he was not athletic to begin with. And he got really into cycling, and until like a week or two into it, he's like, Brandon, I'm going to be a professional cyclist. And I was like, Tim, you're not going to be a pro cyclist. But he kept trying and he made it to semi-professional. He made it to a semi-pro cyclist. So he had like some endorsements. It wasn't great. It was enough. So he made it to becoming a semi-pro cyclist. And he was so energized by that accomplishment that he was like, you know what? I think I can do college now. And so he went back to the community college. And unlike all the other semesters before, he actually got A's at all his classes. He like believed in himself. And so he did that. And then he's like, all right, I can do better than the community college of Rhode Island. And so he went to Clemson. And then after that, he went into ministry. So he went to seminary and now he's a pastor. So yeah. But I'll tell you, in high school, he was a lot of fun because he was completely irresponsible. I was only partially irresponsible. He was completely irresponsible. We once got into a major fight. We were at the library. I don't know why we were there. And he wanted to use my library card to get a book out. And I said, no way. No way. It's like, come on, I'm your friend. I'm like, you're gonna lose that book. He's like, no, I won't. And we got into this big fight. Eventually his sister got the book out for him. Guess what happened? He lost the book. He had to pay a fine. Back then, I knew he wasn't going to be reading books. Tim, if you ever find this video on the internet, I'm sure you're laughing. Hope it's okay if I just start working on here. You should all have this printout. And online students, you can find this on OneNote and look at it instead of my screen if that helps. I'm just going to slowly work through parts of it rather than rag on my friend Tim nonstop. Yeah, I had an unusual group of friends. There's my friend Tim, who failed college. And we had a third friend that was part of a group, our friend Andy, who went to Harvard. Talk about different types of people, huh? Andy went to Harvard. So Tim and I would go there, visit him. Kind of say stuff. Oh, look at all these smart Harvard kids everywhere. Do you know 48 is divisible by 3? It is. It's x plus what? 16 right there. How's it going? Yep. Yep. Okay, good. Yeah. How's it going? Good, you got your critical points. Don't mind me staring. It's part of my job. Just look over your shoulder, see what you're doing. Big brother wants to know. Yeah. How's it going? Yeah, that's.
He's amazing. No, stop.
You came unmuted, Sydney. I
Yeah,
don't know why
someone on
though.
my microphone and said something. It's okay.
Oh, it's all right.
It was Cece.
Oh, okay. Well, all right, yeah. Hi, Cece. Oh, I thought you were waiting for me. Yeah, let's do some intervals here. Andy's a pastor too. Sort of. He works for InterVarsity. He's like a campus pastor, but at like I forget where. Somewhere in New England. Somewhere. I'm the only one who's been able to evade the ministry of our friends. Even my friend Frankie became a pastor. Even him. If he told me that when we were teenagers, I'd have been like, sounds like a really bad idea. Okay. All right. Sometimes when you're lazy, which I know never happens to you folks, you can look at something and be like, hey, it's 3 negative negative, it's positive. I don't know what 3 times 17 is off the top of my head. Okay, I do. It's 53 or 51. No, it's 51. But sometimes you can just figure out what it ought to be. All right, and this one, like a -1, that looks like it'll be easiest. How's it going? Uh-huh.
Oh, no. So,
I don't remember offhand. I should get my solution here. Find out. You should just have two intervals, negative infinity to -8 and -8 to infinity.
okay.
Yeah, so you don't have a second order critical point at 0. Oh, you're gonna try to fit it all in there anyways. Okay. Yes, I'm glad to see you purchased a notebook, though. That's a good improvement. How's it going? Yeah, yeah. I'll admit, okay, for me, this is not the most exciting type of problem. This isn't like sliding ladders or anything like that. It makes sense, yeah. It's just, you gotta be really good at bookkeeping, basically. You gotta make sure you don't make a mistake. Oh goodness, do I know what -16 cubed is off the top of my head? Of course not. Should be able to do this though. So I'll have an 8 times root of the 8. Leave. It'll be, gosh, it'll be 2048. It seems like a big number. It is, yeah. Well, I've done the first kind of part. I figured out there's a local max at -16. And its Y coordinate is 2048. Computer science majors, you can do this by putting everything in binary. Everything is a power of 2 there, 2 to the 11. Yeah, Avery, yeah, you can do it that way, 2 to the 11. And there's a local min at 0 and its Y coordinate is 0. So there's that. Okay, now I just gotta do it for the second derivative. I really didn't mind Chapel too much until the end, where he asked you to stand if you wanted to be humble. It's like, look, it's just not how I roll. I mean, I want to be humble, but I'm not going to stand for it. Doing fine until that moment. All right. Well, I got the following for my intervals of concavity: negative infinity, -8 is concave down, -8 to infinity is concave up. So I've got an inflection point. At x equals -8. Now I just gotta plug that in, right, into my second derivative. No, into my original function. Can I do that one in my head? I don't know. That's gonna be 64 times 16. So that's 2 to the 6 times 2. That's 1024. Is that what my notes say? It is. 1024. All right. And if you look at the graph or the axes I gave for plotting this, you'll understand why they're so weird. All right. Now what's the limit? All right, this is probably the part you don't like. All right, does anyone want to hazard a guess at what this limit as x goes to infinity is going to be? Positive infinity, right? Really just matters what the coefficient is. Right now, what's the limit as x goes to negative infinity? It will be negative infinity, yes. All right. And that's all. Now I leave it to you to plot that. And I can check your plots if you want me to check them. That includes you online students, if you are able to visually show it to me. Or if you're a cheater, you could just plot it on Desmos and check that way, but don't do that. Oh, very nice plot, April. You did it. Good job. Ooh. Somebody has an electric scooter. That looks like fun. Yeah, I just saw him cruising on the sidewalks. Yeah, yeah. I've been wanting to get one of the wheels. Have you seen those? The single wheel? Or you just sit on it and you lean forward? Oh, that looks like fun. It looks like you'll die doing it too. It's one wheel. The one wheel. Yeah. Have you ever used one? Does it feel like death is upon you? Like you're like, wow, I'm leaning forward and I'm not falling into the pavement? Like that? Yeah, that. Yeah, but when they, okay, yeah, it'll try to keep you from falling. You'll fall. Interesting. Well, huh. So I'm looking at my data. I've got a local max at -16, 2048. So I look for -16 here, 2048, I put a dot right there. And then my local min will be at 0, 0, right there. And I will have an inflection point. Where was that inflection point? Right there, -8, 1024. So I'll plot that in purple. There we go. And I want to know my intervals of concavity. It's concave down to the left of -8 and concave up to the right. So I believe I used orange to signify concave down. There. I used green to signify concave up. There we go. All right. So I find it's easiest to actually work from the middle on back out sometimes. So here's an inflection point, and this is where the concavity is going to change. It's going to go from, well, here it's concave down, and I have a local max there. So that sort of signifies to me that I should have a curve that's going to look like that, so that that red dot looks like a max. And then as I go down here, it should look like that. That's nice and concave up. And what do you think should happen after this? What should happen to the right here? Yeah, it should be concave up and increasing. And here, concave down and decreasing. In fact, it'll go to -infinity. So yeah, that's the rough sketch you should have gotten. How are we doing on time here? We got 2 minutes. So one thing I want to go over briefly is a problem from the last slide pack that I skipped very quickly. Very quickly. It's number 4. It says, sketch the graph of an increasing function so that the second derivative changes from being positive to negative at 2. So I'm doing kind of this first part. I want an increasing function so that at 2, it goes from the second derivative goes from being positive to negative, and then a little bit later I need something similar but a change at 4. All right, so what does that mean? An increasing function whose second derivative changes from positive to negative at -2. Well, because the second derivative is changing, right, at -2 or at 2, this sort of tells me that there is an inflection point at x equals 2, right? That's what it's telling me. The concavity is switching from concave up to concave down. All right, and what am I told? I'm told that this is an increasing function. So the concave up shape is this, right? And it has kind of 2 portions. It has an increasing portion and it has a decreasing portion. And the same is true for concave down. It has an increasing portion and a decreasing portion. And so what I want to do is I want to draw something that is concave up and increasing, and then concave down and increasing. So the general shape I'll get will be maybe something like this, where it'll be concave up, 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 and increasing right there and when I hit my inflection point, and then it'll be concave down and increasing. And so that's a perfectly fine picture so far. And then to finish it in the next part, I gotta move it down because I didn't plan this well. So scooch that down there. For the next part, I need it at 4 to go from concave down to concave up, and it's still increasing. And so what I need is another point of inflection. And I'll stick that here. So there, this is concave down and increasing, and then this is concave up and increasing. You see how I was able to draw that curve? You'll encounter a problem like that on your homework eventually. Okay, that's it for today, everyone. Any questions online, students? Nope. All right, I'll see you folks later. Bye.